Hello everyone and welcome to I609. We will start today with a very quick introduction to unconstrained optimization. So what exactly is unconstrained optimization? And the keyword here is unconstrained, which means literally there are no constraints on what what could be the allowed values of variables. So let's just write what it is. So mathematically it can be written as finding the minimum value of a given function f of x over all possible x. Sometimes to emphasize that the problem is unconstrained, we just also say that x belongs to Rn, which really means that x can take any value in the Euclidean space of n-dimensional variables. So that really means that consider all possible vectors x of size n. So x is a vector which has n components, and these components could be anything, any real number, and out of all possible vectors, we would like to find that x which gives us a minimum value of this function f. Okay, so the function f is given as an input, and today we will actually try to appreciate what does this really mean when we say that f is given as an input, because f could potentially be anything. So let's first look at examples and then come back to this question about what it means that f is given as an input. So here's a very simple example. I would like to minimize the value of this function 3x1 plus 7 times sine of x1, where x is a one-dimensional vector, and this is a very simple problem. I think most of you would be able to say that this doesn't really have a minimum because x1 can go as low as possible, and you can get a value as low as possible, or whatever arbitrarily low value you can think of. You can achieve that value for this function. But this is a problem, so we will say that this is an unconstrained problem in one variable. Here's another problem in two variables. Plus 4x2 square minus 12x1 plus x2 plus 8, and suppose we would like to find the minimum value of this function. So if I want to minimize fx where x belongs to R2, that means I'm looking at all vectors of size 2 and I would like to find that vector which minimizes this given function. Now some of us should still be able to solve this example by writing it as sum of squares or taking some derivative and so on and so forth, but this is obviously slightly more difficult than solving example 1. And some of these problems may have a very obvious answer, but as we add more nonlinearities or more complications to the function, it starts becoming more and more difficult to solve. So for example, let's look at a third function of only one variable again. So this is the earlier example is in two variables. Example 3 could be this function minimize an exponential function e to the power of minus x1 square plus cos square x1 plus log of x1 square plus x1 by 12x1 square plus 1. Okay, so obviously this function is a bit hard to imagine in our minds, and even thinking about what could be its shape or whether it is defined at all points is not so straightforward. So how should we go about finding the minimum value of this function? So this is again a problem in one variable, but arguably it is slightly more difficult than example 2 because of so many terms and nonlinearities involved. So it's not very obvious that you can always say that two-dimensional problems are more difficult than one-dimensional problems. So in the nonlinear world, things are not very simple and obvious. Okay, let's look at a couple of more examples to see how these nonlinear functions could look like. So let me write an example 4. So again, a problem in one variable. So this is an absolute value of some linear term divided by another absolute value. Okay, so again, like example 3, it's not very obvious how this function looks like and where the minimum could be. Okay, so far we have been looking at examples where all the functions were somewhat nicer, in the sense that functions were compositions of simple functions, even though the final function looks a bit complicated, but at least every part of the function is sort of a simple function. For example, an absolute value, or multiplication, or some exponential, or some cosine and sine. But things don't have to be like that. Your function could be defined in some convoluted or complicated way. So, for example, again in one dimension, suppose my function looks like this: 12 times cos of x1, which is sort of a nice function. It is just one trigonometric function, but the second term could actually be an integral 0 to x1. Let's say sine y1 plus e to the power minus y1 square cos of y1 divided by 1 plus y1 square dy1. So now even evaluating the function at a given point is difficult. So suppose I ask you, forget finding the minimum of this function, let's try to just find the value of this function at, say, x1 equal to 1. So it will not be that simple, because to even evaluate my f at a single point, I will have to solve for an integral, and many times integrals don't have closed form solutions. You might have to resort to some numerical schemes to find the value of the integral itself. These integrals could be in one dimension, they could be in multiple dimensions, which makes the problem even more difficult. So even when you say that I have a unconstrained problem in one variable, it could be extremely difficult to solve.